So all the lectures should be, if I don't do that, again, remind me in the beginning of class every time, because I have forgotten sometimes. So what I plan to do is, okay, so what I was thinking is, so there are a lot of people, so now 37 people in the meeting, and actually in the team there are about 50 people, 50 plus in fact. I don't think that so many people will stay. Uh, so the administrative things such as I mean, so there will be weekly homeworks, there will be some midterm, maybe one or two, and then there will be final. But details of those can be discussed with a smaller number who stay after 1 or 2 weeks. On the other hand, but if there are any things people want to ask before they to know about the course, you can ask now also. Is there any question that anybody wants to ask about the course in general? Okay. So if not, then fine. So we will start. So as I said, so maybe we'll do these administrative things a bit later after the number of people reduces. And yeah, so generally speaking, so there's my, so in the, so you can go to my homepage. So you will find the old homepage of this. I have taught this course.
Sir, you are muted.
Sir?
You appear to be muted. You'll have to go back to the meeting and unmute yourself.
Sir, you are muted. That might be his connection.
I think it is.
Hi, I just spoke to Professor Manjunath. So apparently his internet failed. So he said he'll try getting it back on by 4, else we'll adjourn to Thursday. Thank you. Could you hear me or can someone?
Yeah, yeah, okay.
Hello.
Oh,
This is Manjunath. Actually, the internet has come back, but it is a very spotty one. So, hello.
yes, sir.
Yeah. So the internet actually it may be spotty. So it may happen that it will get cut again. In which case we will just abandon, and I will try to make arrangements so that this doesn't happen on Thursday. Okay. So, well, sorry about that, but yeah, I guess it can't be helped. Okay. So let me continue. So what I was saying was, as I said, so if it gets cut again, we will just abandon today, and just wait. If I get kicked out, wait for me for 2 minutes, and if I don't come back on Thursday.
Sir, you appear to be muted again. Plus, your voice was cracking up.
But I just I unmuted, but I don't know why it got muted again. Okay, so now I'm unmuted. So yeah, so one thing I said was if I get kicked out by this internet failure again, wait for me for 2 minutes or 3, and then just abandon. If I don't come back, we'll reconvene on Thursday at 3:30. I will make some arrangements for that by then. Okay. So let me just start. What is yeah, so two things. One, there is a TA. So probably at some point he will later this week he will. There
Could
are.
you please start recording?
Yeah, I started recording, but there are only 6 people in the meeting now. Is that right?
No, there's many.
There are 37.
Oh, is this a different meeting then? I don't know what happened then. No, in this meeting it says only 6. Okay, well, are there 37 in the meeting? There used to be. Okay, but it says it is recording. It says top.
Yes, we can see 37 already.
Okay, but it also says it is recording. Is that?
It is recording.
Okay. Okay. So, and is it still shared, this OneNote?
No.
I don't think so.
Okay, so that I have to probably do. Okay, I shared it now.
It's visible, sir.
It's visible. Okay, good. Okay. All right. So, okay. So, yeah, so the TA will get in touch with you people at some point of time, and to fix I mean, there will be a tutorial. So, and solving problems is important, etc. So it is a good idea to attend the tutorials and so on. So anyway, he will schedule that later. And so as far as books and references are concerned, you can go to my old homepage. So from my teaching page, you can go there and then see the old page. There are a bunch of references. In particular, there is a book by Stein and Shakachi. Stein and Shakachi have a series of books called Analysis something. Okay, each one has a different title. Some 4 books in analysis. So this one is on real analysis. It's an excellent book. And then there is also a book by Bogachev called Measure Theory. So there are actually there are lots and lots of books in measure theory. So you can choose whatever you like. It only matters what topics we cover. So I don't follow any book very closely. Now, pretty much all books are very close to each other in some sense. The same subject, it's the basic stuff. But I don't follow one book very closely. But so that's why you keep track of what topics are being covered, and you find whichever book you like most. It doesn't matter, more or less. If you want to check with me, you can check with me. Particularly, these books are excellent. Stein and Shakachi's book is very nicely written also. And Bogachev's book is more extensive. If you like to know more than what I do, then you can look at that. Or there are many, yeah, so there is innumerable books in this. Anyway, that is the thing. Okay, so what is measure theory? Okay, so let me go to the one. So what is this business of measure theory? What is this subject and why are you here? Okay, so measure theory is about studying length, area, volume. So it is studying length, area, volume, etc. So it's not something new for you. So you have studied these things, lengths and areas and volumes before. In fact, in high school you would have studied, of course, how to calculate. I mean, so the square is declared. A square of side length 1 is declared to have area 1. And then you try to find the area of various other things like a rectangle with B and A, then the area is A times B, and then you find all sorts of trapezium, etc. You find where parallelogram and so on. Okay, so you do that in high school. So you would have found, and the way you do it is basically you cut them. Either you cut your the shape that you are interested in into pieces and somehow make it a, if you can arrange it so that you get a as a union of squares, then you get the volume of area of what you want. But then how do you measure the area of some irregular shape like this? Okay, so you have some shape like this or maybe a leaf. So how do you measure the area of this inside here? Okay, so the part inside, how do I measure the area inside? Well, it's not new either. You have done that. So in your calculus class, calculus or analysis class, you would have done Riemann integration. So you have all studied integral calculus. So this was the whole point of integration, right? So what was integration? About finding areas. So if you have to represent your, suppose you have a function f on some interval a to b, and then you want to find the area under this. So this was the area was what we call the Riemann integral of f from a to b if it exists. The area here is this if f is Riemann integrable. So you have already done this. So all sorts of irregular shapes also you can measure the areas of. So what is new? It's not new. It's going further along the same lines. But there are limitations to these older methods. So the high school method is of course very limited. It works for very few shapes. But integral calculus is a very powerful piece of mathematics, and you manage to cover a lot of regions this way. You can measure areas of many different things. However, not everything. What measure theory does is goes beyond this, and we measure areas of many more things which you could not make sense of in the Riemann integral. So here the statement that there is this if here, if f is Riemann integrable, and that puts kind of a restriction on the nature of f. If f is a continuous function on a closed interval, it's certainly Riemann integrable, no problem. That seems at first to be sufficient. Why not? That's good enough. That covers a lot of shapes. What more could you want in life? Well, you can always want more. And measure theory is about trying to find areas of more things. Okay, so goes beyond Riemann integral to find these areas. I just write areas, but you could also do lengths, volumes, depends on the dimension you're working in. Later we will just call everything measure. Okay. So, but find areas of more general classes of sets or larger. So we want to calculate areas of as many things as possible. Okay. So what is the problem? For example, so in Riemann integral, can we calculate what is the length of rational numbers as a subset of real numbers? What is the length of the subset of rational numbers? Does it make sense? Okay, so this is the type of question. If you have never seen it, it probably looks weird. Yes, we are used to length of an interval or something like that. We can understand that the length of some interval like 0 to 1 is 1. That we understand. But what is length of rational numbers? Or can we make sense of it? What about length of something like the Cantor set? Can we make sense of that? Can you make sense of the length of the Cantor set? Cantor set, I assume everyone knows. If you don't, you should know what Cantor set is. It is a very important object, also a good thing to think for counterexamples. So let me quickly recap. It is a strange, well, hardly strange by the kind of standards we are going to look at, but at first, when you see it, it is a rather strange type of set. The simplest Cantor's 1/3 set starts with the closed interval 0, 1. So that is K naught. And then you cut the middle 1/3 of it. So you take 1/3 to 2/3 and you delete the open part of it. So you get K1. What remains is 0 to 1/3 union 2/3 to 1. And then you delete the middle 1/3 of the remaining intervals. And you get things like K2, which is 0 to 1/9 union 2/9 to 1/3. So now you have 4 intervals. And then union, what is that? 2/3 to 2/3 is 6/9 to 7/9 union 8/9 to 1. Okay, so and so on. So you understand how it goes. So this, so the intersection of this Kn is K. This is the Cantor's, the standard Cantor set, Cantor's 1/3 set, let's call it. So there are other things you can do, different proportions and various other rules of deletion. But this is the simplest one, 1/3 Cantor set, which is where you delete the middle 1/3 of each interval. And the intersection of Kns is this set K. Okay, so this is the, so you show that what are the interesting things about it. It is an uncountable set. It is quite a big set. It has no isolated points, but it does not, it's a compact set. It does not contain any interval. Okay, so those, so it's called totally disconnected because it's a compact set, closed set. It contains no intervals at all, but it has lots and lots of points. So this is a strange looking set. Can we make sense of the length of the Cantor set? What is its length? Okay. So that those are the type of questions which Riemann integral does not answer those questions, or it will tell you that no, we cannot measure the length of rationals. That's what it says. But here we will be able to do that. Okay, so that is one set of things that measure theory does for you. it goes beyond Riemann integral to calculate lengths and areas inside the familiar territory of real number, the line, the plane, and the space. Okay, so you calculate length, area, and volume, right? So that's what you do. Okay. Now, but that's not all. I mean, it also goes beyond. Okay, so this is one of the things. This is already something big. So what else does it do for us? So I'm giving an overview. So it's not a very systematic overview. I'll just tell you a couple of things. The kind of things you could ask, I mean, can we measure areas inside other sets? I mean, so here, these are all inside Euclidean space. But can I measure volumes inside some other spaces? Can we measure areas or volumes inside other spaces? So what are other spaces? So there are two different kinds of things I have in mind. So for example, let us take something like you take U of n is the set of n cross n unitary matrices. Okay, so everyone knows what unitary matrices are, right? They are n cross n complex matrices such that A star A is identity. Right? So you can take some within that. So if I give you a subset of that, can you measure areas? So if A is a subset of unitary matrices, example, A could be all the set of A in all unitary matrices such that
it's 4 o'clock.
So A is the set of all unitary matrices such that, I don't know, let's say A11 is in minus half to half. Now I just wrote down some silly set here, but you can think of all sorts of subsets. The set of orthogonal matrices is a subset of unitary matrices. So can we measure what is its relative volume? So if I say that the total volume of the unitary group is 1, somehow I normalize somehow that the unitary group should have volume 1. What is the volume of the orthogonal group inside it? What is the volume of this set of unitary matrices which have first entry in minus half half? What is the set of what is the volume of the set of matrices which have one eigenvalue which is equal to 1? Okay, all sorts of such questions can be asked. Is there a notion of volume inside these spaces? Okay, so that is one of the questions we can ask. Can we measure areas or volumes inside other spaces? Okay, so here is another space. So one example is here. Let me give another kind of example. So is the question clear? Or I mean, please ask questions. So if you want, so I'll occasionally remember that you are also here and that I may ask you to ask questions, but I may forget. So you can also interrupt me and ask questions. That is okay. So is it clear what I'm saying? Of course, none of the answers are clear, but I hope it is making sense that you can ask the question of areas and volumes inside other sets. Is that okay? Okay. So here is another class of objects where I may want to measure. So here RD is finite dimensional space. So let me take some infinite dimensional space. Let's take C01. It is the set of all functions from 01 to real numbers such that f is continuous. It is the space of all continuous functions on the closed interval 01. So is there a meaning of volume inside this? of subsets of C01. What are subsets of C01? I could look at the unit ball, for example. The set of F such that norm F is less than 1, where this norm means the supremum of Fx, absolute value. Sup of Fx, x in 01. So that is the norm of a function. So let's say the unit ball in C01, what is its volume? Is there a meaning to such a thing? Or I could take the set of all F such that you have seen weird functions. F is nowhere differentiable. I'm just putting down some random subsets. That's all. There is no. But the question is hopefully clear. Is there a meaning to the notion of volume of subsets of C01? Is there any such thing? Can we make sense of such a thing? Or if so, how? Same for under space of unitary matrices, or we can consider other sorts of spaces where we can ask for volumes. Okay. So there is yet another kind of space. So these are different in a way that it may not make sense to you, but the examples I have putting down here, they are different types of things. It doesn't matter to you. As all that matters to you is the question even a meaningful one? Is it worth asking? And if you don't feel so, you should tell me. Then maybe I can convince you, or maybe not, that it is a good question. These are good questions to ask. You can ask within, so you can ask in some strange spaces. So for example, so my space itself can be Cantor set. So length inside Cantor set. Okay, so let's say K is the 1/3 Cantor set that we had. Okay, so the picture is here. So this is so what happens in 01, you delete the 1/3 to 2/3 open interval, then delete the middle one open 1/3 of each interval that remains, and then you take the intersection of all the remaining sets, and that gives you the 1/3 Cantor set, right? So that is 1/3 Cantor set. Now, what I'm interested in, not what is the area of, what is the length of K. That was what I was asking in the previous question. So first question was measuring lengths, areas, volumes inside Euclidean space. So there my question would be, what is the length of the Cantor set? Now I don't ask that question. My universe is the Cantor set. Can I ask about lengths of Cantor? So let's say the length is declared to be 1. Okay. So suppose we say that its whole length is 1. So what is the length of? So suppose I take length of K. So to give a sense of what I mean, I want to measure lengths of subsets of Cantor set relative to the Cantor set itself. So here the goal is want to measure lengths of subsets of K. So if you want, I'll put relative lengths of. It's always relative. There has to be some standardization to measure length, area, etc. In basic high school, we fix the area to square to have area 1. There has to be some standardization. It's always relative. But can we make sense of some relatively? Can we talk about lengths of subsets of Cantor set? For example, length of K intersection 0 to 1/3. Okay, let me take a vote here. So can someone, anybody is welcome to unmute themselves. What would you say is the relative length of K intersection 0 to 1/3? If at all it makes any sense. It's up to you.
Would be half.
Half. Okay, so somebody says half. Any other options? 1/3. Anybody for 1/3?
Yeah, I'd guess 1/3, I guess.
1/3. Okay, so why would you say 1/3?
I mean, some sort of notion of the Cantor set being sort of distributed across the interval 0, 1, and then you're taking 1/3 of it.
true, but I'm not taking a third of the Cantor set. So you see, Cantor set has nothing in 1/3 to 2/3. So K intersection 0 to 1/3, by the way, is the same as K intersection with 0 to 1/2. Because the Cantor set has nothing here. You agree? In the first step of Cantor set, what do you get? In the first step, we get K1, which is a union of these two. So K intersection 0 to 1/3 is exactly the part of Cantor set which is here. There is an identical sort of part on this side, which is just a translation of that. So it seems, so whoever said half is right. I mean, it seems to make more sense, right? I mean, so yeah, when you see 1/3, you might think 1/3, but because Cantor set is not sort of uniformly inside this whole interval, we have deleted the entire middle third. This should have got to be half. This is not the spelling of what? What is the spelling of what? O-U-G-H-T. Okay. One half. Okay. That we believe, but it is not so. I mean, this is a nice enough set, but maybe there are other sets, so it is not so clear. So for other sets, it may not be so clear.
Is it actually half or what?
Well, yeah. So is it half? Well, we don't know. Is there a notion of area length within the Cantor set? Yes, there is, and it will turn out to be half. Yes. But here, what I want to say is whatever be the notion of length, you will reject it if this was not half. See, we are asking for definitions. We are not asking, these are asking for definitions. You have to, when we ask for more areas and lengths and areas of more sets, you have to define it. The only question is, okay, then I'll define anything. But no, it has to be reasonable. What is reasonable? Then we have to be more open about what we want. Only then we can be clear. For example, if somebody tells that length of rationals is 5, okay, they better have some reason to back it up, right? Why is this holy number 5 showing up? Okay, so similarly, anyway, so we have some expectations in mind. In case of Cantor set, at least you would probably agree that if at all there is a reasonable notion of length, then this should be half. And indeed, we will later see that it is possible to measure lengths inside the Cantor set, and that measure will give half to this. But it will not give just for this set. It will give for all sorts of subsets of Cantor sets, not all set. And it's not so trivial what other subsets of Cantor set should have. Even just as it is not clear within Euclidean space. For example, what is the length of Cantor set inside Euclidean space, inside R? We don't know. I mean, maybe you know, but at the moment we don't know in the course. So it is not clear. So these are the type of questions. So
Sir,
yes.
sir, I have one query.
Yes.
I'm not getting like how K intersection 0 to 1/3 equal to K intersection 0 to half. Like it should be K intersection 0 to 2/3, right? Because we like 1/3 to 2/3.
What you say is also true. This is also equal to K intersection 0 to 2/3, but let's be careful, not closed, open, because, well, 2/3 itself is there in your Cantor set. So if I put open 2/3, then yes, it is also equal to K intersection 2/3. So does that, I mean, okay, I got less than what is true. Maybe that is what confused you. Is this okay?
Yeah, like how half is coming, that is not clear to me. Like how, like 0 to half.
If you agree that K intersection 0 to 1/3 is same as K intersection 0 to 2/3, then that is also K intersection 0 to half, right?
Oh, okay, yeah, I got it. Yeah. Thank you.
Yeah, no, I was saying less than what is true. That's what I meant. So sometimes I confuse students by writing 2 less than equal to 3, which is perfectly true, but it can be confusing. People ask, why don't you write 2 less than 3? Well, it is also less than equal to. So similar way, I just, yes, I wrote that. So what I'm saying is that K intersected with open 1/3, 2/3 is empty. Therefore, I can extend this K intersection 0, 1/3 to something in between. Doesn't matter. So the reason I put half there was, so there was this candidate answer that K intersection 0 to 1/3 should be 1/3 because you are taking 1/3 of the interval, but it's also K intersection 0 to half. By that logic, it should also be half. Or for that matter, it is same as K intersection 0 to open 2/3. So it should also be 2/3. No. Since it has nothing here, the symmetry consideration tells you that K intersection 0 to 1/3 should have half of the length of whole of K, whatever that be. That is what makes more sense. So I just wrote this to justify this answer of half here. So similar things can be done.
Okay, got it.
You got it? Okay. Great. Any other questions? So by the way, so also so it takes a little while for me to again get used to this online teaching and for you to get used to. So let me know if the writing is not clear, shabby, small, etc. I mean, or if you want me to speak more, explain, and tell me. Okay. So I may not be able to satisfy all the demands, but I will try because I have, even in normal class, I really have absolutely no clue how to teach because students are there and I do something. I don't know whether they are following, not following, etc. unless they tell me. And in online class, it's even worse. So unless you tell me, I will just do whatever I want or whatever I can, which is not necessarily what I want, but I don't know what else I should do. Okay, so let me know if for any things, any of these logistical things or writing, etc. So this OneNote should also be shared on the Teams page. I'll figure out how to do that and do it later. At the moment, it's not shared. Okay. Anyway, the recording is there. So the Cantor set is there. So for fun, let me tell you some other things like Cantor set. I don't know if you have seen this before. There are also higher dimensional Cantor sets, which are what are called fractals. Okay, so you may have heard the word fractals, or maybe you have even seen this. So what are higher dimensional Cantor? So what is Cantor set in 2 dimensions? There are many choices. One is like this. You start with a triangle, equilateral triangle. Okay, so this is supposed to be an equilateral triangle. What you do is you connect the midpoints of the sides and delete the open triangle which is in the middle. Okay, so you get 3 triangles. What remains is this one, and this one. 3 triangles remain. Each of them is an equilateral triangle. You can punch a hole in each of them. So what I am shading is not part of the set. Just like with the Cantor set, what I am shading is what is removed. I always remove the middle open 1/3 triangle. Okay, I mean, sorry, the middle triangle, the open triangle I delete. So shaded part is removed. So next stage we'll delete these small triangles, lots of them. I won't write all of them like this. We go to each of the remaining triangles and do it. And then again, you have an intersection of compact sets, and by the finite intersection property of compact sets, we get a set here that so what comes in the end is what is called Sierpinski gasket. So it is one analog of Cantor set in 2 dimensions. There are other analogs. So we could start with a square instead of a triangle. Divide it into 9 parts, right? So I'll just mark the endpoints here. So I draw lines like this. Okay, so maybe I actually draw them. This is 1/3 I draw so that it divides into 9 equal squares. I delete the middle third. This is like Cantor set, or middle 9 or whatever you call it. The middle triangle square I delete. Now all these squares are remaining, but I do the same game in each of them. I go to each of these squares. I delete the middle 1/3. Okay. I go to this square, delete the middle 1/3. And same here. I delete the middle 1/3 and so on. So in the end, again, as you go on deleting and so on, you get a sequence of compact sets. Always delete the open square. Okay, so that what remains is always compact sets. So intersection of compact sets is going decreasing sequence of compact sets. It's going to be non-empty. And like the Cantor set itself, it will have those properties. It will be an uncountable set having no isolated points. And but it will contain no open set because you are pretty much punching holes everywhere. So you don't get any open set inside it. So this thing is called Sierpinski carpet. Okay, so I hope if the definition was not clear, I mean the picture is not clear, let me know. But this way you have lots of sets like Cantor sets in higher dimension. You have more choices. There are many such things one can make. Relative areas of things within the Sierpinski gasket. First of all, what is the area of the Sierpinski gasket itself is a question. Okay, so it is like asking, I mean, it's a bit like what is the, so if you make a chapati with radius 4 centimeters, you can ask what is the area of the chapati. Let's say the thickness is 0, roughly speaking. So what is the area of chapati? We know how to do it. But what is the area of a dosa, which has holes everywhere? Okay, so what is exactly the area of a dosa? So it is not so clear. So this Sierpinski gasket is a somewhat triangular shaped dosa, you can think. It has lots of holes. Okay, worse than that. Yeah, so you can ask two types of questions. So I just put them down to introduce you to some interesting objects if you have not seen them before. Plus tell you that you can ask the same questions here, two types of questions. One is you can look at Sierpinski gasket sitting inside R2. And you can ask what is its area inside R2. Right, that is what you can do. Or you can take a subset of the Sierpinski gasket and you can ask its relative area relative to the Sierpinski gasket. So this question, Sierpinski gasket area, is like my asking what is the length of the Cantor set. Relative areas of subsets of the Sierpinski gasket within the Sierpinski gasket is like this one, where I was asking what's the length of K intersection 0 to 1/3 within K. Similar question. So you can do the same in Sierpinski carpet and so on. Is there a notion of areas within these objects? So these are also questions of measure theory that will naturally come. Okay. So first and foremost, so just to summarize, so I was telling you that measure theory is all about measuring lengths, areas, volumes, and in more general settings. So for one of the most important things is to do it in the Euclidean space itself in the as complete a form as possible. As we want to revisit, we want to go into this notion of length and area so much that never again in your life do you have to come back and ask what it is. That is one thing. So staying within Euclidean space, that itself is a very important part of the subject. But when we understand these, we also go a bit more general, and we'll have very general notions of volumes, areas, and so on. So maybe we'll talk a little bit about these types of things also. Okay. So this is what the subject is about, sort of. But it is also more. Okay. So let me give further motivation. But before that, any questions, comments so far? For some reason, I still see 13 people as participants. I don't understand this. So it's very puzzling. So,
We see 38.
okay, so it's a bit strange. Well, okay. So any questions so far? I mean, this is, I was saying about measuring areas and so on. That's what the topic is about. That's what we are going to study. But just like you studied, I mean, so what is integration? So this is, you can say, one part. So this is part one. Areas, volumes. But just like Riemann integral was there, so we will have a new notion of integral. See, the notion of area and integral are intimately connected, right? So there are two ways. Just let's go back to your Riemann integral and the old notions of areas that you had. Okay. So one is that in one sense, integration is a more general form of area. How is that? So let me just write here. So why do I say that? Okay. So suppose you want to measure. So I have the plane and I have some region inside the plane. Let's say this is R2. So for some reason I have written like this. So this is a area in R2, and I want to measure the area of that. So that area of A, if it can be done in Riemann integral, is the same as integral of a function So area is actually, you can write it as integral A of xy dx dy, double integral. What is this? We are saying that you take the function this is the function on R2, okay, which takes the value 1 here, and 0 outside. Okay, so you take a function which takes the value 1 on A and 0 outside, and if I integrate that, okay, assume that the Riemann integral exists, then that will give you the area of A. In that sense, integration, what does it do? More generally, this is areas are very special case of integrals where your function takes only two values, 0 and 1, right? So the value inside A is 1, the value outside A is 0. So this is integral of a function which takes two values. The function takes two values, it makes only two measurements. It's like a yes-no question. But integrals are that way integrals. So this is integral of a function that takes two values. So in that sense, integral is more general, right? Because you can also integrate functions which are not taking two values. I mean, you can integrate a continuous function which takes infinitely many values. So in that sense, integration is more general than lengths, areas, volumes. On the other hand, integration is also, you can almost say integral is a special case of areas, volumes, and so on. Why is that? That is by the picture that I said earlier. So think of a function like this. Its integral is the area, I mean, in under the graph, right? So similarly, when I want to think of a function on R2 and its integral, it is the volume of the graph under that. So you go one dimension higher. So in other words, areas of sets inside RD is a special case of integration of functions on RD. But integration of functions on RD is a special case of finding volumes in RD plus 1. Do you understand what I'm saying?
Sir, could you please repeat the last point?
So your voice is not.
Yeah,
clear.
I was for some reason I was kicked out of the meeting and I'm back. Yeah. So yeah, I really need to make some. Okay, let.
Sir, you're muted again.
Okay, sorry, I was muted again. So can you see the shared file?
Yes.
Yeah.
Okay, it looks like no one is able to hear me for some reason.
Uh,
We can hear you.
Yeah, you can hear. Can you see the shared OneNote or not?
Yes, sir.
yes.
Yes.
Oh, you do.
Yeah.
Okay. No, I was wondering whether it was also cut. So whether I have to share again. Okay. So then let me go back and I'll repeat what I was saying. So what basically I want to say is that measurement of areas and volumes and integration are really inseparable from each other in the following sense. Already in Riemann integral and the older notions of area, we have this because so if I want to measure the length of a, so all I am saying is if the measure of a length, not constant function one, the function which is 0 outside, 1 inside. So that is the integral of that is gives me the length. On the other hand, if I but integration is about integrating more general functions also. But the integral of a more general function can be thought of as area in the higher dimension, in not in one dimension, in higher dimension. So what I was trying to say is that volume in measuring volume in RD is a special case of integrating functions on RD, but integrating functions on RD is a special case of measuring volumes in RD plus one dimension higher. So in that case, in that sense, integration and areas are intimately connected. Okay. Consequently, so when we do this more general notion of areas, which you have not seen before, so to speak, so the areas beyond, when we extend that notion of areas, we also end up extending the notion of integration. So just to be clear, I'm telling you what the course outline is. So one of the things is I said it is about areas and volumes, but much of the course will be talking about integration, which is the same thing is all I want to say. Okay. So we will have a more notion. So in this course, we end up with a more general notion of integral than more general than Riemann integral. So this thing will be called Lebesgue integral. Lebesgue is one of the names that will keep coming again and again. So I'm just dropping the word here. So this will be called Lebesgue integral. And it is a very powerful notion of integral. What it can do is it can integrate lots of functions which you could not integrate with Riemann integral. Okay. So this is a much more general notion of integration. Again, we will first do it in RD, but it will go to very general spaces. We can talk about integration, but just think of RD. So this Lebesgue integration is a very general notion, much better than Riemann integral. And once you go there, you will never come back to Riemann integral. You don't need it. Okay, so Lebesgue integral is sufficient for life. You don't need, that is the most general notion of integral most of us will ever need. So this is one of the main things that you will learn. Okay. So in short, it is measure and integral. That is the topic of the thing. So in what way is the Lebesgue integral? What way? I mean, what was Riemann integral look good enough? What is so bad about it? Okay. So what is bad about it? Let me explain that. So already I explained in terms of areas that there were things that you could not measure volumes and areas of. That's okay, but that doesn't mean that what you had was bad. So the thing is like this. So one way to explain. So by the way, this is an overview lecture. In some ways it is easier, in some ways it can also be harder, because when I give overview, the technicalities will not be there. We are not doing anything technical, but on the other hand, we go over many things. So you have to understand, view the subject from a broader global point of view some way. Otherwise, so here, if you don't follow all the details.
Sir, one query.
Okay. Yeah. Question.
Sir, here in the drawing, you said that inside area is 0 and outside 1. But if we integrate something, so we should get some values, right? So like how it could be 0 inside that point I did not get clearly.
So can you? So you mean that thing that I defined, or this picture that I have here?
Yeah, this picture. Yeah. You told that
So I
inside is
take a
0.
function. So the indicator A is a function which is 1 if that point x comma y belongs to A, and 0 otherwise. Okay, so this is the function. So that's the integral, Riemann integral of that function, which gives the area of A. Okay, what is the question? Can you now repeat?
So if we integrate, then we'll get some value, right?
Yes.
Like you told that inside is 0 and outside it's 1. So that
Right.
is that term.
Maybe it got cut. I did not hear the full thing. Can you please repeat?
Like you told that inside is 0, inside area is 0, and outside it's 1. Like
No, it is 1. Oh, okay, if I said that, I said it wrongly. It is 1 inside A and 0 outside A.
okay, thank you. Yeah, got it. Yeah.
Okay, it's 1 inside. Okay, maybe I misspoke. So then when you integrate, you get the area of it. Yeah. So of course, I'm thinking of a bounded set and all that here. Okay. So all that I did with all this was that integration and volumes are intimately connected with each other. Now I want to say in this course we'll end up generalizing the Riemann integral to another notion called Lebesgue integral, which is fantastic. So it is a great thing. So you will be very happy when you learn this. So okay, I hope so. Anyway, so what was what was the I mean, did you feel the lack of Riemann integral? Was it sometimes waking you up at night that alas, this notion of integral is not good enough, there must be something better? Maybe not. It never woke me up, but one can see what Riemann integral is lacking in a different way. So this is another sort of motivation for this subject before knowing it. Okay, so let's look at the set of, consider, let's define R to be the set of all f from 0, 1 to real numbers such that f is Riemann integral. Okay, so let's take that set, and then on this I want to define a norm. Okay, so if you want a metric, so let's define the metric. So integral 0 to 1, I take fx minus gx, absolute value. You know from basic Riemann integral theory that if f and g are both in here, they are Riemann integrable. F minus g is and its absolute value is also. So this makes sense. So is this a distance? Is it true that it's a metric on the real, on this, sorry, not on R. What have I written? On the space of Riemann integrable functions. Let me call it X. Yes?
Yes.
Is it a metric? Is it symmetric? Symmetric is clear. D of fg and d of gf are same. Will it satisfy triangle inequality?
Yes.
This is okay. And d of fh less than equal to distance of fg plus distance of gh. Is this true? This is also true, easy, because when you do this, you get fx minus hx absolute value, which is smaller than or equal to fx minus gx absolute value plus gx minus hx absolute value. When you write it out, you will see that. So what else is needed? It should be non-negative. Is okay, right? With equality, if and only if f equal to g. Is this true?
Yes.
No.
Yes.
I mean,
No? Okay. So if no, then
So we actually need continuity, right?
no, we are not assuming continuity. We are taking Riemann integrable functions.
Okay. So if you don't assume continuity, then this result is not true, right?
So then it is not true, because you can have two functions which have whose difference. So this metric can be 0. So this is false, because example, you can take g to be the 0 function and f to be 1 if x is half, let's say, and 0 if x not equal to half. Okay. So then you can have, so you can make up lots of. You said continuity, so yeah, you can take a function, instead of making it left continuous, make it right continuous. You get a different function, and then you get, but the Riemann integral will be 0, of the difference will be 0. So f minus g is 1 at x equal to half and 0 elsewhere, and if you do the Riemann sum business, you will see that this distance is actually 0. So it's not quite a metric. So it is a pseudo metric. So it is, no, it is what is called a pseudo metric. Okay, it just means nothing other than that these two are satisfied, the last one is not satisfied. Distances can be 0. When such a thing happens, actually this is not a problem. So I said I'll talk about a shortcoming of the Riemann integral. This is actually not the shortcoming. This is just a prelude to come to the shortcoming. This is not a big deal, okay, because okay, all right, we have some functions, so one can make it a metric. So what do you do when you have such a thing? Can you get a metric space? So there is a general way to one can get a real metric by some quotienting with respect to an equivalence relation, where I declare f equivalent to g if their distance is 0. So you take the distance 0 as an equivalence, and you see that it's actually an equivalence relation. It is symmetric and it is transitive. Therefore, it gives you an equivalence relation. You can quotient x by that. In other words, you take the equivalence classes under this. So x is the set of equivalence classes. So let's call it x hat. I don't want to elaborate on this because this is not quite to the point I want to make. I mean, this is you can do this always. Whenever you have a pseudo metric, you can do this. You can quotient with respect to things which are, you can take the equivalence where two things are equivalent if they are 0 distance, and then quotient by that, and you get a set of equivalence classes. On that, you get d hat. You define of two equivalence classes as d of fg. It is well defined precisely because, in other words, if I want to measure the distance between two equivalence classes, I take one representative of each and I take the d of them. And because of the nature of the equivalence, this doesn't matter which it doesn't matter which representatives of the equivalence class you pick, you always get d hat. So this x hat d hat becomes a genuine metric space. In other words, it will have d hat will be symmetric, it will have triangle inequality, and d hat of two equivalence classes won't be 0. There will be nothing with no two distinct equivalence classes will be at 0 distance. Okay, so this way, this is a very general thing. So that this is not the problem. So what is the problem? What is the shortcoming of Riemann integral? So the shortcoming of Riemann integral is that this is not complete. Not complete. I will leave it for you to come up with an example. You remember what completeness in a metric space is. It means all Cauchy sequences have a limit. So you can find a Cauchy sequence here which does not have a limit. So that is the shortcoming. Why is that a shortcoming? I don't know. I mean, you probably have seen completeness in many classes, right? I mean, you have seen it. Okay. So why is, I mean, there is a general notion of how you can make a completion, an abstract way you build Cauchy sequences and so on. That is there. But first of all, why is not being complete a problem? It just means that your space is not the real full space. You are looking at it in a bad way. So when you are working with, for example, rational numbers, you realize that you are working in a somewhat limited environment without even, if you go outside, you can see all real numbers, then you understand, of course, that rationals are only a small part of it. But staying within rational numbers, you can realize that your view is limited because your space is not complete. You have Cauchy sequences which are going into a black hole where you don't know what is happening. So you realize that there must be something more than the world I see around me. So then you try to fill those holes and then you get real numbers. Similarly, once you see that this space is not complete, it means that it is lacking something. There is, of course, the abstract notion of completion, which is not very useful directly. So the thing is to realize what is it that it is missing. Okay, what is it that is this space is missing? And one of the highlights of this course is when we come to this Lebesgue integral and we do this entire exercise with Lebesgue integral instead of Riemann integral, the corresponding metric space will become complete, which means that it is good. You are not missing anything. This is the space in which you want to work. Okay, it is just like, so just like going from rational numbers to real numbers. So maybe what I said here was not entirely clear, or this was a motivation. So to say that in Riemann integral was lacking something would have been a priori clear by looking at this metric. And this Lebesgue integral takes away that problem. And since it becomes complete, you never need a more general notion of integral. That's what will happen. So this is one of the things that we will do. Any questions, comments so far?
So I have a doubt.
Yeah. So by the way, I don't get to see who is speaking. So is that something that? Yeah, go ahead. Anyway, who is this?
This is Siddharth.
Okay, go ahead.
The problem of not completeness, could it just be because our choice of metric was bad and not our choice of space itself, that f could still be Riemann integrable? That's how we can construct our set. But maybe the distance between f and g could be some other thing.
Okay.
With the Riemann integral.
There are other metrics which could very well be complete, but don't. This is a good notion of a distance, an average distance on C01, for example. Let's take C01, which is a subset of this. Even on C01, there is a natural metric which is the supremum of fx minus gx, absolute value. Right? That is one distance, but that may not be always the right distance. That is a kind of worst case distance. Whereas sometimes you may want an average distance. How far are f and g on average instead of what is the worst distance between f and g. So in which case, isn't this a natural enough looking distance? That is an average notion of distance between f and g. But you are right. So if you are in the sense, well, this is not what you meant maybe, but this tells me there are other notions which if you have seen some probability and so on, maybe then it is more natural, or even electrical engineering, whatever else. So there are other notions. Instead of this, you can do
Yeah,
this.
this is what I had in mind.
Okay. So this is more natural. Yeah. Why is this more natural? See, it is just if when we have a vector v and a vector w, v1, v2, vn, w1, w2, wn, we measure their distance in Euclidean space by taking the differences in the coordinates and then take sum of squares and square root. So this is very much like that, except that our vectors are now infinite and indexed by 0, 1. So I think of this as an infinite vector fx, a function we think of as an infinite vector indexed by 0, 1. So the coordinates of this vector are fx, values of the function, and the coordinates themselves are uncountably many. So G is similarly another vector. Then the analogous notion would be fx minus gx squared. You can't sum them, you integrate them and take the square root. Now this is a good distance, by the way, but you can't take f Riemann integrable. You have to take you cannot take this on Riemann integrable functions. What you can do is you can take R2, which is let's call it x2, which is the set of f from 0, 1 to R. Is Riemann integrable. Take that space. Take the set of functions whose square is Riemann integrable. On them, you can define this distance. Okay. Okay. If this is your question, good, because everything I said works for this also. If you do this with Riemann integral, this space is not complete. Okay. Firstly, it's a pseudometric. You do quotienting to go get a genuine metric space, but still it's not complete. And once we go to Lebesgue, the corresponding analogous thing in Lebesgue will be complete. Okay, so everything applies here too.
Okay.
Okay, this is that answer?
Yeah.
Okay. Any other questions? Okay, so if not, let me continue. So okay, this is so we will do measure. We'll do talk about measure. Measure is the more general form of area and volume. We'll talk about integration with respect to measures, which is this Lebesgue integration. And third part, I don't know how much we will be able to do this. Whenever you have integral calculus, integration is very intimately connected with differentiation. So is there a more general notion of differentiation? Okay, I will just leave it by saying this. So if Riemann integral is very intimately connected with the usual derivative we have, right? So now we have a more general integration. What is its connection to differentiation? Do you also have a more general notion of differentiation, which is, so to speak, an inverse operation of integration or whatever else? So that also, I don't know how much I'll be able to touch upon this, but this is also an important point that we do get slightly more general, we'll get a more general perspective of differentiation. Let's put it that way. That differentiation will be a more subtle thing here, but it is there. And it is related to integration, like within the fundamental theorem of calculus. So that also is there. Okay, so but we'll let me leave it at the moment at that. So my goal is, well, I don't know how much time I'll get for this differentiation. We'll at least touch upon one or two theorems there, but we'll spend much of our time on this measure and integration. Okay, so okay, before leaving the motivation part, but why? Why do you have to have this subject? Okay, what is the purpose of this subject? Why is it there in your curriculum? Why are you being made to learn? Well, of course, it in one sense you may say it looks nice, but there are many nice things in math. Why is this necessary to learn? Okay, so there are two kind of reasons which for which measure theory is almost a compulsory course. So you go anywhere in the world, at least at graduate level, it is a compulsory course. Now there are two reasons why this is the case. So one of them is, so there are two reasons. Measure theory course is taught. So one is it provides the framework for probability theory. What do we mean by it provides a framework for probability theory? See, probability theory, I mean, all of you would have seen some basic probability, tossing coins, throwing dice and stuff like that. That seems it doesn't, I mean, there may be difficult problems, there may be very difficult combinatorial problems, but there does not seem to be any doubt about what we are talking about there. But it is not so for more involved probability problems. For example, throwing a dart. So here is a dart board. And you are completely at this board. So what is the chance that the dart will fall in this quadrant? Okay, if I ask that question, most of you will agree that it is 1/4. So I'm assuming you are completely unskilled dart thrower, but unskilled, but you will always hit the board. Okay, so that's a strange kind of unskilled person, but you're an unskilled person who will definitely hit the board, but beyond that you have no clue where you are hitting. So this is a random experiment of the kind considered in probability theory. Okay, this is so if we take that notion, so what is the chance it will hit in the first quadrant, in this second quadrant? Most people will agree it is 1/4 by symmetry. Just the same way you said that the length of 1/2 this Cantor set should be half. Similar considerations will tell you this. Or if I give you, so let's say this radius is 1. And this is 1 and this is half. What's the chance that I will hit the inner disk of radius half? Again, you will probably calculate that, okay, it should be proportional to the area. So you do the area of the inner one by the area of the outer one, so you'll get 1/4 again. So it's kind of clear, but the point here is exactly this. So that the probability you are doing by calculating area. So this is probability is intimately connected with area in this example, right? Because if I ask for some region, what's the chance you will hit there? You will tell me the area of that region by area of the full disk. That seems to be the correct. But then the more general notions of area, all the questions that we asked here also become relevant for probability. So can I ask what's the chance that the dart will hit a rational number? I mean, a point with rational coordinates. Okay. It's not going to be useful in a casino, but you can ask that question anyway. So what's the chance that it will hit a Cantor set? You fix a Cantor like set, Sierpinski carpet or something inside. And then what is the chance that the dart I throw will hit inside that set? So you can ask that. Anyway, the point is the probability notion is intimately connected to area, and any understanding of area will lead to a better understanding of probability. Indeed, that is what happens. So probability was, so once measure theory was discovered, it was immediately one of the first things all the founders of measure theory realized was this is somehow going to put probability on a proper mathematical framework. Before that, it seemed like a loose connection. People used to still do these calculations on intuitive basis, but it was not always clear what is the basis. So what measure theory does is gives a framework for probability. We will not see probability theory in this course at all, but if you ever take a probability theory course, then you will see that the mathematical framework of it is measure theory. Okay, so that is one reason why we teach probability is a subject of much importance in both pure and applied areas, and so it is so this provides a framework for that. Okay, second, it so what by it I mean measure theory. Another reason is actually intimately connected to something I was telling here about completeness of these metric spaces. Okay, it provides the right framework in which to talk about solutions to let me write solutions to what? Solutions to some problems on function spaces. So what kind of problems on function spaces? So example, it could be PDE. Differential equations are problems on function spaces. What you will be solving something like d by dt f of t comma x equal to say this is a PDE. Okay, if f is a function of two variables and we want the time derivative to be equal to 2 times the space derivative, whatever it is. It's a famous equation. Problem in function space. What is that? So we are f, right? So that's a problem in function space.
It's 5 o'clock.
Oh, okay, it's time. So I will stop in a minute. Okay, so I'll stop in a minute or two. So another kind of problem is, let us say something like an isoperimetric problem. Find the region of area 1 with the smallest perimeter. So what you are talking about is you have to draw a curve in two-dimensional plane, which is maybe a closed, simple closed curve. And then what you want is the area here should be 1 and the length should be minimized. Okay, so that's another problem in function space. So a curve is a function from the interval to R2. So you're talking about problems. So it doesn't matter what these problems are, but how is measure theory helpful here in all these things? The point is these are very difficult things. So you want to solve in a huge function space. Is there a solution? First question is there a solution to this? Is there an F which satisfies such a thing? Or is there a region which minimizes the perimeter given us area should be 1? So is there such a so existence of solution, uniqueness, these are natural questions to such problems. Now how is measure theory helpful here? The point is in all sorts of problems it's always usually easy to get approximate solutions. Okay, it is well, okay, let me not explain in this context, but it is easy to get approximate solutions. Let's just admit that it is sometimes possible to get approximate solutions, and you want to take approximate solutions and take a limit to get an actual solution. But that is where the completeness helps. So you may have so for example, so maybe I'll tell you in a very toy situation, you are trying to solve x square equal to 2 in rationals. You can find approximate solutions. You can find rational numbers whose square is approximately 2. You can find many such things. Now, one way to try to solve this problem is to take a limit of the solutions and get the answer. The thing is, inside rationals, you would not get a limit. Whereas inside reals, that's exactly what you would call the solution to this problem, which is square root of 2. So a similar thing happens in this here. All sorts of problems on function space, you have approximate solutions in nice spaces of functions you already know. But when you take limits, they will go outside of the spaces. For example, you may have had it in nice continuous functions, but when you take limits, they just go out. When we do Lebesgue theory, we will come to spaces which are complete, and then you will actually find solutions within the space. Okay, sorry, I went a couple of minutes over time, so I will stop now. And if there are, I will stay for a few minutes if people want to ask questions and so on. Next Thursday onwards, we will actually go into the subject matter, start from the beginning. Okay, if you didn't follow parts of this motivation, it is okay. We will be able, I mean, so that's just motivation. We will start from the beginning. Okay. Okay.